In this section, we'll study optimization problems, and we'll try to solve them using the method of Lagrange multipliers. In the last section, we got this claim: the gradient direction is the direction where the function changes fastest, more precisely, increases fastest. Here we'll begin with level curves. See this example. Consider the unit circle, the circle of radius 1, and then the equation is given in this way: x squared plus y squared is 1 squared. Okay, we name this portion by f of xy. What can we say about the gradient of f? Okay, to answer the question, we introduce the parameterization. The curve can be parameterized as in this equation. R of t is a vector, x of t and y of t. And x of t is cosine t, and y of t is sine t. And t is moving from 0 to 2 pi. So that is the circle of radius 1. And here, and start from here, t is 0, pi over 2, t is pi, and 3 pi over 2, and 2 pi. Once x and y are functions of t, then we may consider capital F as a function of t. So let's try to get derivative of f with respect to t. Now we are using the chain rule. First we make x derivative and xt derivative, and y derivative, and here yt derivative, and this is constant, so it must be 0. Now we collect f sub x, f sub y to be gradient of f, and xt derivative is minus sine t, and now y sine t, t derivative is cosine t. Okay, for a point on the curve, that is xy. Now this one, the vector must be cosine t, and minus, okay, not minus, sine t. Okay, cosine t, sine t, okay, like that. Now, so that direction is this one. If we rotate, then now change the position and put minus, so that is exactly this one. So minus sine t, cosine t, that one, the vector is 90-degree rotation in counterclockwise. So that is now that direction. This is that one is that direction. Okay. But this equation is saying that gradient of f and the direction, the vector, dot product is 0. Means that gradient of f is orthogonal to that direction. So the choice is this one. Okay. Practically, we can get gradient of f, and x derivative is 2x, and y derivative 2y. So exactly from here to there, that is gradient of f. Here, geometrically, the gradient is normal to the curve, because that one is tangential vector, so that must be a normal vector. And the gradient of f is directing the fastest increasing direction. Inside, the value is less than 1 for x squared plus y squared, and along the curve, the value is 1, and outside, the value is larger than 1. And along that direction, value is increasing fastest. So we considered one example, but we can generalize this observation here. It's always true. Given a level curve f of x equal k, the gradient vector, gradient of f, is normal to the curve and pointing the fastest increasing direction. Now we are ready to consider optimization problem with equality constraint and introduce an effective technique. We try to maximize f of x subject to g of x equals c. That means that x must be chosen satisfying this equation, and among all x points, and now we try to measure the maximum value. That's the problem. Here, look at this picture. Now, this one is, now that one is z equal f of xy, the surface. Okay. Now, we try to maximize this function, and with the constraint, this curve is on xy plane. So we have to choose the point from all this curve, and we measure the function value, and among them we can choose the maximum. Pictorially, this point seems the largest value. Right? Now look at this contour plot, and this one is contour, and with D1 large value, and D2 and would be smaller, and now D3 is small value. Now along these contours, and here we already know that the gradient of f is normal to the curve and pointing the fastest increasing direction, so that these arrows are the gradient direction along the contours. Now here the constraint g of x y equals c. Also, if we try to make gradient, then the gradient must be normal to the curve and must be the fastest increase direction. But for this one, we don't know which direction is increasing direction. However, once we have maximum, okay, the corresponding point to that one is this one, then here this contour and that curve should tangent each other, so that gradient of f and gradient of g must be parallel. We don't know is the same direction. However, they must be parallel to each other. So we have this conclusion, and maximum two gradients must be parallel because they tangent each other at the maximum. Okay. So from this geometric observation, we can get the method of Lagrange multipliers. For the maximum and minimum values of f subject to g of xyz equals c, now we consider functions of three variables. Find all values of xyz and lambda such that gradient of f is lambda gradient of g, because they'll be parallel at maximum or minimum, so that along with a constant we can express this equality. And here this is constant. We have to decide four variables, x, y, z, and lambda. Now we have four equations. In 3D, the gradient will make three equations, and this is the equation of constraint. So we have 4 equations. So that we can solve the problem reasonably. Now, after finding all values, all points and lambda, now by using xyz, we evaluate f at every here points and try to get the largest one for the maximum and try to get the smallest one for the minimum. That's the strategy. Let's go to example. A topless rectangular box is made from 12 square meters of cardboard. Find the dimensions of the box that maximizes the volume of the box. Okay. Let's draw a picture for the rectangular box. Okay. Here, that is a rectangular box. And now, okay, let's go down. And here, like that. So if we, for this length is x and width is y and height is c, then the volume will be xyz. Now, here, xz is the area of the front side and back side. We have another one, so 2xz. And for this side and right side, the area is yz, and another one over there, so the 2yz. Now xy is area of the bottom, but we want to get topless rectangular box, so that here only we have one of xy. Total area must be 12. So we have this equation. It will be used for the constraint, and that is g of xyz, and there's f of xyz. Now we'll use the method of Lagrange multipliers. Okay, gradient of f equal lambda gradient of g. Okay, here x derivative is yz, y derivative is xz, and z derivative is xy, and lambda and g x derivative, that is 2z, right? X derivative, then it will be 0, and plus y. And y derivative, then that will be 0, and that is 2z, right? And then y derivative will make x here. Now z derivative, then that is 2x, and plus 2y, and the last one must be 0. Okay. Now, this equation is not easy to solve. Of course, there's 3 equations, and there is the 4th equation. Now, to solve it effectively, let's try to explore some symmetry. We'll try to multiply here for the first one, x, and for the second one, we try to multiply y, and for the last one, we try to multiply z. Then this will become xyz, again xyz, again xyz, so that the values are the same. Then we may get some hint and strategy. Okay, we'll do that. So here, by multiplying x, we have x, y, z equals lambda. Okay, for the first one, we multiply x, then 2xz plus xy. For the second one, we multiply y, then it's the same, and lambda and y is multiplied 2yz plus xy. Okay. Now we multiply z, then again xyz, and lambda, z is multiplied 2xz and plus 2yz. yz. Right? Yeah. Okay. So once lambda is non-zero, then here, because this is same, these two must be the same, right? xy is the same. Now, of course, over there, to make a reasonable volume, xyz must be positive, so that these two are the same, left-hand side the same. If lambda is 0, then right side is 0, so at least one of z must be 0, then volume becomes 0. So physically we know that lambda cannot be 0, and x and y and z must be positive, right? Okay. So that's reason. Now this is same, and these are same, so this must be same, which means that, okay, this is equation 1, equation 2, equation 3, and there is equation 4. Then from 1 and 2, we can get here, okay, x equal y, right? How about 2 and 3? Okay, 2 and 3. Okay, left-hand side is the same. Lambda is non-zero, so the right side must be same. Now this one, that one are the same, so it must be same. Now x is common, so that y must be 2z. So from here, y must be 2z. Here we have now x equals y and y equals 2z. We get that one. How can we complete the computation? Now we have to use that one. We have never used it so far. Okay, so we'll use that. Here, now x is 2z, y is 2z. So that plug over there. So from 4, we have x is 2z, y equal 2z. So we try to make everything as a function of single variable z. X is 2z, so the 2 and 2z, x is 2z and times z, plus y is 2z, 2 times 2z and z again. Now, okay, there's z. Okay, now the finally xy, 2z times 2z, right? That must be 12. Okay, from here, 4z squared, 4z squared, 4z squared, so that 12z squared, that is 12. That means that z squared is 1, z must be larger than 1, so that z must be positive, so that z must be 1. Then x and y are 2, right? So from here, x and y are 2, so that now the volume xyz, so the maximum volume xyz equal this one, xy are 2, so that 4. That's the final answer, right? Find the extreme value of f of xy equal x squared plus 2y squared on the circle. Now, this one is constraint. That is the function. Again, we start with gradient of f is lambda gradient of g, and we have that. So here we separate three equations, and 2x is lambda, 2x is lambda 2x, and now 4y equals lambda 2y, and the constraint x squared plus y squared is 1. Now from equation 1, and if we move this one to the other side, then it becomes 2x and now lambda minus 1 equals 0. So we have either x equals 0 or lambda is 1. If x is 0, okay, Okay, that is. If now x is 0, then now we can use this equation. Then y squared equal 1, which implies y equal plus minus 1. For x0, we have y plus minus 1. Now, how about lambda is 1? Lambda is 1. Then, for this one, just there's no information. But once lambda is 1, then from equation 2, we have 4y equal 2y. That implies here y equal 0. Now the constraint, by using third equation, we have, in this case, now x is plus minus 1, right? So on the circle of radius 1, now, we found 4 points. Once x equals 0, then y is plus minus 1. This is a minus 1, plus 1, plus 1. Once y equals 0, so it's horizontal x-axis, then x is plus minus 1. So we found 4 points. And like over there, the strategy is we have to find all values of the point and lambda satisfying these 4 equations. In two-dimensional case, we have 3 equations, and now we try to evaluate f at all these points and try to get the maximum and minimum, right? Okay, we found these points, and here, okay, from this one, the function that is now x squared plus y squared, twice of y squared, x is 1, y is 0. So that here f is 1. Of course, over there also the y f is 1. Now, how about this point? X is 0 and y is 1. So that f must be 2 at the point. And again, this one is f is 2. So minimum value is 1 and maximum value is 2. Okay. Okay. Now we do a continuation from the last one. Okay. Now we try to find extreme values of f of xy, the same, but rather than the curve, now the domain is inside and curve and inside of the unit circle. Now, and only, but we already know that along the boundary, here the value is 1 here, 2, 1, 2, like that. So values are between 1 and 2 along the boundary. How about inside? For inside, we may try to get the critical point and try to find the critical value. Okay, so now we get gradient of f, that is here 2x and 4y equals 0, which means that x equals 0 and y equals 0. That is critical point. At the point here, f is now 0, right? So inside, the extreme value is 0, which is minimum value. So that along with this one, here f is 0, and this is minimum, and that is now maximum, f is 2. Okay? Okay. Here we look at the method of Lagrange multipliers from a different angle. For the optimization problem, here, maximum of f subject to g of x equals c, the method finds values of x and lambda satisfying this equation. Now, we'll try to interpret this method by using calculus. In fact, we made this formula from geometric observation. Now we'll try to interpret it. Now it can be interpreted as follows. Find the critical points of this function. Now f of x minus lambda and g of x minus c. So start with that function. In the theory of optimization, it is called Lagrangian. So start with the Lagrangian, and we try to make a derivative. Okay, this one is derivative with respect to x, so that one will make here gradient of f minus lambda gradient of g, and this is constant, so it will disappear. And we try to make a derivative with respect to lambda, then this will be remained. Now we equate the right side to be 0, like that. Then here we can obtain that the method of Lagrange multipliers. So that in practice, in optimization theory, we will work with this Lagrangian. Okay. Okay, we'll continue in the second part. Thank you.